So, welcome to the ATN seminar today. Our speaker is Sara Scaramuccia, who will be talking about monodromy in biparameter persistence modules. So, Sara, the floor is yours.
Thank you, Bastian, for the introduction, and thank you for the invitation to have this talk. This talk is a joint work with Octave Morten from the École Normale Supérieure in Paris, and today we will talk about monodromy in biparameter persistence modules. So just a little bit of motivations. Monodromy is something already studied in the context of persistent homology, precisely from the group of Patrizio Frosini. There is a work by Cherry, Etienne, and Frosini in 2013, which is mainly restricted to the case of homology of sublevel sets of functions with two values in the context of matching distance or coherent matching distance. As you can see from this nice video they made at that time, on the right we can see two classes, two pairs in the persistence diagrams of a line reduction in the biparameter space, which is in the middle, and monodromy is the phenomenon where we have two dots swapping when we do a loop in the parameter space. So we are changing the line of our one parameter reduction, and it happens that the two dots are swapped when we go back to the initial point. And we need to do the loop twice in order to recover the initial situation. And what we want to do today in this work, what I want to talk to you about, is a way to translate the notion, the definition of monodromy at the level of persistence modules, to take advantage of generators and relation, to take advantage of the presentation of a module, and try to see what is the behavior of monodromy at that level. And a broader question might be, but it's not, we won't answer to this question, but I think it will be, it is in general interesting to ask ourselves whether or not the monodromy can say something about the choice of invariants we have in multi-parameter persistent homology, because we all know that there are many possible choices for invariants in that case. And I think that the algebraic setting, so talking about monodromy at the level of persistence modules, can help in leading the way in this sense. So monodromy, it's a topological notion which is not strictly speaking related to persistence, and it is related to the presence of a covering. So we have a big space X and a covering map down to the base space B. The map is supposed to be a local homeomorphism, and for each point in the base space in B, we have a neighborhood, so that the pre-image is simply the disjoint union of a discrete class of sets. And as you can see on the right, there is a trivial notion of covering. So the first case is a trivial twofold covering. So simply I have two circles projected down to a single one, and if I take the pre-image of a point, I simply have two different neighbors, and if I do a loop down in the base space, the two neighborhoods stay separated. On the right, we have a non-trivial monodromy, because we can follow the blue dot and the green dot around one single loop, and we will find them swapped. So we need two loops to go to the original situation. More precisely, the monodromy group is the group action induced on the fiber by the fundamental group in the base space. And this is the general notion. And one of the purpose of this talk is to link this general notion to our setting. So try to understand which space is X, which space is B, which one is the covering map, and so on. So along this talk, we will review some very standard notions, definitions of persistence modules, structure theorems, interval modules, something I think you all already have encountered, but I simply put them all in my notation. And then we will talk about line parameterization of a biparameter persistence module. So except from the first point, everything is restricted to the case of biparameter persistence modules. And we will, and this part will be important to arrive to the definition of monodromy. And then in the very final part, I will tell you some results we have found so far for monodromy. Everything in this talk is not peer reviewed. It's preliminary work. We will upload it in a short time in archive. So please, if you have any doubt, if you see any mistakes, please interrupt me. So the general setting, we have the notion of P persistence object in some category C. P is a poset, and a P persistence object is nothing but a functor from P to C. That is, we have an object in the category C for each element in the poset, and whenever we have two comparable elements, X and Y in the poset, we have a map induced, which behaves nicely with the composition. For the case of persistence modules, we select as the poset. In the case of single parameter persistence, for instance, we can select the real numbers, only the positive ones, if we like. And the category C is the category of finite dimensional vector spaces over a field. And in this setting, we know that we can present a module by indicating generators, G1, Gn, and relations, here denoted R1, Rm. The important thing is that we have a way of, we can consider the free module generated by an element, so the cyclic modules generated by G will be the module that in any step after X has the simplest vector space F with dimension 1 and 0 otherwise, all the maps are the identity, and so on. And we can describe every module M as a quotient of the free modules generated by the generators and the relations. So in general, also in the single parameter case, we can present a module like that It's a little bit weird, but we can do it. We can indicate one generator G, another generator H, and then relations like that. The important thing in this work, we consider only discrete modules. That is, modules that have changes in their steps, in their elements corresponding to the elements of the poset, only in a finite number of elements, C0, Cn. And for the rest, they are stable. So we call discrete modules something like that. In the biparameter case, we have that the definition is the same. We have only to update the definition of discrete because we need a grid, a finite grid of elements in the poset where the module can change, but the presentation of the module itself is the same. And as an example, on the left, you can see a module generated by two generators, G and H, with these degrees, and where you see the red X, you see a relation, meaning that in one case the two generators have become the same, or one the G generator is 0 here. And as you can see, the shape of a module can be very much more complicated. In this category, as everybody knows, we have a notion of morphism, and here I just wanted to highlight two kinds of morphism. The 0 degree one, which is the general morphism, that is, we have a map in the category of vector spaces for each degree, and all the squares commute, but we can also consider degree D morphism, that is, we select a degree maybe in multiple, a multi-degree, okay, sorry, and we can ask the same requirement for this square, where each map is going up by D in each degree, but the definition is the same. We will call this one a D morphism. As an example, just to visualize how the notion of a morphism behaves in the case of presentations, we have a possible morphism between these two persistence modules like that. We have the two modules with the two generators in the same degrees, but what changes is the relations. And we can simply map the generators one by one, and this provides, in this case, a morphism, which is surjective, not injective, because we have this part in the domain which is non-trivial, and it's sent to 0. I highlighted this case because it's not possible to define a morphism the other way around, but we can do it if we allow for delta morphisms. Because if I simply map the generators backwards, so L to H and M to G, this is not compatible with the relations. And so I need to jump a little bit and, for instance, map L to phi L. So I move plus 0, 2 vertically. And this way, I don't have any problem with the relations. This way, I have a delta morphism, which is injective. So it's kind of inverse, but it's not an inverse. Just this was just an example. In the case, of course, I can do a morphism in one direction and I have an inverse in the other direction, and the two of them are zero morphism. If the composition is the identity, of course, they are isomorphic, but it's not always the case. And talking about isomorphisms, we all know that in both cases, I mean, if I have P equal to R plus or P equal to R2 plus, I do have structure theorems, but the two theorems are very different in the single parameter case or in the biparameter case. The single parameter case is very known to everybody. What is important to highlight is that I can decompose any persistence module like that into a sum of persistence modules which are cyclic and which are simply described by two numbers, the degree of the generators and the degree of the relation of that module. So if I start with a bad presentation like the one I introduced before, I can simply manipulate my module and make it into the bar form, the barcode, and everything. So here, because of the structure theorems, we have the invariant we all know. What changes in the multi-parameter case is that we also have essentially unique decomposition into indecomposable, but we don't really know the shape of the summand in the decomposition. For instance, as you can see in this image, the two modules I presented before are indecomposable and are much more complicated to be described. I mean, I need two generators. I need for instance, especially in the left one, in the one on the left, there is the darker area where two generators are alive. So I have a non-trivial Hilbert function there, which is neither 0 nor 1. It's 2, and this kind of behavior has led many researchers in this field to introduce what is called interval modules, which is a simplification of all the potential persistence modules we can have. By interval module, we mean a module whose support, that is the shape, the portion in the poset with the non-trivial vector spaces is convex and connected. So here in this slide you can see that in the right hand side you have an example of an interval module, because we have the support of the module, the blue area, which is convex and connected, whereas in the left hand side we have a support which is not even convex, and moreover there is this darker part where the support is more complicated. We have two copies of F there. Both of them are not decomposable. So there are situations, there are proposals in the literature where some results are stated in terms of interval decomposable modules, and the restriction is not I mean, it's effective. We are skipping many modules. So now we restrict only to biparameter persistence module, and we are we have to talk about the line parameterization, the line restrictions we can take into account whenever we have a persistence module. These line restrictions are already known, but in terms of this notation, they can be restated like that. This is precisely the same definition made by Frosini et al. So we can consider a line depending on two parameters A, B. A it's related to the slope of the line. B is the intersection with the anti-diagonal. And we can simply consider the restriction mt tilde of this module according to one parameter t, and then rescaling everything so that for lines depending on parameters a, b, such that a is below 1/2, in practice we are considering the first coordinate of the restriction, so x1, and for the lines with a over 1/2, we are considering the other coordinate x2. Moreover, whenever we restrict to a line, we have the notion of a discrete module behaves nicely. I mean, if we have a discrete module and we restrict it, it stays discrete. There is a lot of work for this line parameterization, and there are some invariants in the literature, especially the fiber barcode and the rank invariant, which are very dependent on this idea of restricting biparameter modules to lines. And it's already known that if we change a little bit the line, if we make it varying with continuity, I mean, this variation is continuous, and we simply can restate this continuity by separating the changes for the A, and see that the two corresponding modules are interleaved, and also by changing B and seeing that the two corresponding modules are interleaved. That's okay. What is important for the sake of this talk is the observation, which is the same Claudia Landi did in a work in 2018, that the map with changing associating to each line the diagram of the restriction of M to that line is continuous with respect to the bottleneck distance. Another thing before introducing the monodromy is the notion of duality. I mean, if I take the support of a persistence module, for instance, this rectangle delimited by two non-comparable points, 1, 3 and 5, 2, if I want to see in the parameter space that is according to A and B, which portion of the parameter space denotes a line passing through that rectangle, I can see that those lines are in the yellow area on the right, because all the lines passing through 1, 3 are parameterized in the segment here from -3 to 1 to the level starting from the level a equal 1 and going down to a equals 0. The same for the point 5, 2, and in the middle all the lines, or all the corresponding lines cross somewhere this rectangle. This is important because in order to introduce monodromy, we have to do precisely where we are doing loops and where we are considering fundamental groups and so on. So we restrict to n admissible lines and n admissible diagrams. What I mean by that? I mean that if I fix n, a natural number, there are some directions L, such that the corresponding diagram, persistent diagrams of the restriction, so the diagram ML, has precisely n different points in the persistence diagrams, each one with multiplicity 1. So I don't want higher multiplicities, and I don't want to take care of the diagonal. So whenever I fix n, I can consider the portion in the parameter space of all the lines that have persistence diagrams with precisely n points. And as we can see in this example, the line on the left side has a double point. All the other ones, no, all the other one crossing the darker part have precisely two different points. There is only one single line here in the middle with a double point. So locally, I have this orange area in the parameter space of two admissible lines with the little hole in the middle, because I have to remove this point. So I have a non-trivial fundamental group if I consider this space. And why am I interested in this situation? Because this kind of double point here, the point I remove, I can loop around this point, and qualitatively there are 4 regions separated by all the lines passing through B and D, so the purple lines. I have these 4 areas corresponding to the pictures you see in the bottom part. And as you can see, I can go around and the four regions A, B, C, D, and then going back to A. If I follow the induced path, what I mean by induced path, the path induced but on the diagrams. That is, if I have n admissible lines, I have also n admissible diagrams, and I can follow by continuity all the points in the diagram. And if I do it in the example you see, I go back not with the precise original situation, but if I start here with the blue dot A and the green dot green A, I can uniquely follow all the points going to B, going to C, going to D, and then in the end I have the blue and the red dot swapped. So which means that the example in this example there is the monodromy I want to capture. The idea here is to consider as the covering map the map P going from the diagrams, the ordered diagrams. I mean, I can consider delta plus as a set of all the possible pairs. I am avoiding the diagonal. And P is simply the map between the ordered set of pairs and the diagram, which is not, as we know, the points in the diagram are not ordered. And this map can be proven to be surjective and a local homeomorphism. And I can lift, so for the theory of coverings, I can simply lift a path in the n-admissible diagrams to a path at the level of ordered diagrams. So I can start with gamma, a loop in the admissible line. This would induce a loop in the n-admissible diagrams and a loop at the level of ordered diagrams. So what happens in the example is simply that we have a non-trivial action of the fundamental group in the n-admissible lines pointed at some line. Here in example is the double point, the one with the double point. And this fundamental group is acting on the diagrams by swapping the elements. So the definition we gave is simply is simply a mimic of what we have seen at the beginning. So we have our covering, the action of the fundamental group, and through the lifting we have discussed, we have an induced group homomorphism between the fundamental group and the permutation of n elements. Because the group of permutation is now acting on the copies of the diagrams. The monodromy group is, in this case, the image of this group homomorphism, simply like that. And here, with this definition, we arrive to the results we have proven. And the main result is this one. Whenever we have a persistence module in the two-parameter case, which is the direct sum of two modules, if we fix a direction which is n-admissible, we know that the diagram in that restriction in L is simply the union of the two diagrams, and that is not that interesting. The point is that the monodromy group of M is a subgroup of the product of the two monodromy groups of M1 and M2. This means that monodromy can happen only within a summand. So it cannot mix generators from two different summands in the direct sum decomposition. The idea of the proof is this one. So the first part, the fact that the diagram of M is the union of the two diagrams, is simply it's trivial because they are single parameter modules, and so each single pair has to belong to one of the two summands. That's okay. But this means that if we are considering n admissible direction for M, the same directions are M admissible for the first summand and n minus M admissible for the second one, with M less than or equal to n. And moreover, we can we have proven this this lemma, which simply tells that the map associating to each direction the cardinality of the diagram except the diagonal. So with all points counted with the multiplicity is a lower semi-continuous. So we can have jumps because there might be mergings and splittings, but the lower continuity holds. This is also already known. But if we mix the two observations, we know that if we are following a path in the line, we do have that parameter m depending on t, the parameter on the path, is like that. So mt is the cardinality of the diagram at the line gamma t of the diagram of M1, and n minus mt will be the cardinality of the other diagram. By lower semi-continuity, we know that this means that m is constant. And in the end, the proof ends with the commutativity of this diagram. So we have the injection of the fundamental group, which is related to the first part we have seen. We know that we have horizontal surjective maps to the monodromy groups, and we simply proved that this diagram commutes. So in the end, there is what we wanted to show. This is important, this result, especially for a corollary, which is very trivial. I mean, if monodromy can happen only within a summand in a sum decomposition, then if a summand is interval, meaning that there is only in each moment a single generator, it's impossible to have monodromy. So this is the final result. So in the end, what we have found is that we have translated something already known about monodromy into algebraic terms, and we have restricted the possibility of observing monodromy to non-interval indecomposable. And if we address the initial question on the importance of monodromy in selecting invariants for multiparameter persistent homology, we can say something. What we can say? We can say that there are some invariants in the literature which are more powerful when restricted to interval decomposable modules. For instance, in the case of the generalized persistence diagrams proposed by Patel, Kim, Memoli, we know that in general the notion of generalized persistence diagrams comes from the one of generalized rank invariant. So a generalized rank invariant induces a persistence diagram. But in the case of interval decomposable modules, we can also go back. So if we know the generalized persistence diagram, we can recover the generalized rank invariant. On the other hand, interval decomposable modules are powerful, but they are missing something because they are missing all the monodromy parts. And this is more in line with the result by Bauer and Scoccola, where they showed that in most cases, modules are not interval decomposable, in the sense that the space of interval indecomposable modules is dense in the space of all the persistence modules. Monodromy seems to detect something in the discrepancy between the generalized rank invariant and generalized persistence diagram. This is the last example I wanted to show to you. On the left, you see a non-interval module, which is not decomposable. And the two models here in this slide, they have the same generalized persistence diagram, because their diagrams are simply one copy of the eight-shaped big area and the little square. So the two generalized persistence diagrams in the two examples are the same. But on the left, the module is non-interval, and there is monodromy. And on the right, we have simply the juxtaposition of two interval modules. So we have the lighter part below and the square over in a direct sum. The two rank invariant are different, because if you follow the black line, you will find two different barcodes. And I think it's not a case that on the left there is monodromy. So monodromy, we don't know if it recovers all the possible cases where these two invariants are different, but at least there are cases where monodromy discriminates between the two cases, discriminates between what we are missing in moving from the rank invariant to the generalized persistence diagram. So this is what I wanted to tell you. So thank you for listening, and if you have questions, please.
Thank you very much, Sarah. Let's all unmute briefly and give Sarah a round of applause. So I don't see any questions in the chat for now, but if you have some, feel free to mention them now or speak up. Otherwise, I'm going to start with the very simple one, because I like one of the conclusions of the biparameter one. So very naively put, do you think this could be used to kind of inform the design of novel invariants for biparameter persistence modules, if they can differentiate a little bit better? So could you potentially use that in a new representation or in a new representational invariant?
What I think is that monodromy is not something easy to capture, and it's I mean, computationally, I don't think it's very useful, but I think it's a theoretical thing to take into account whenever we are maybe we have the risk of removing too much information, because it seems very related to it seems to be the part we don't want to have in persistence, in all the persistence theories. And if we know better how it behaves, maybe we are more in control of what we are missing. And I think these results go in the same direction of the work of Bauer and Scoccola. I mean, maybe it's too much to go to interval modules. Maybe, I mean, this is my feeling. It's not from the scientific part. The only result in this talk is that we cannot have monodromy between two different summands. And this is not, I mean, I don't have at the moment an interpretation of this result. It's something I keep in mind whenever we need to simplify multi-parameter persistence, because we need to simplify it in any case. But maybe I mean the interval module definition is something very natural. It's a one simplification very natural to ask. But the density argument and the complete removal of monodromy, I don't know, maybe it's too much.
See, interesting. Thank you. Yeah, it's really interesting. I think we have another question by Henry.
Yes, very nice talk. Very interesting. So, I mean, you stressed the theoretical importance of monodromy and keep it in mind. But even though it's difficult to compute, are there maybe heuristics? If I give you a a two-parameter persistence module, are there heuristics for trying to find monodromy?
I think that I mean, I did nothing in the computational part of these things, but I think that the general level is I mean, the peak of our knowledge is still the work of Frosini, Etier, and Cherry. I mean, it's in the sublevel setting. They have done some ways of computing effectively approximations of one parameter reductions and so on. I think that another aspect of this work I like is that if we translate everything into algebraic terms, maybe we can also observe a monodromy with other tools. There is Rivet, there are other things. And up to now, my feeling was that monodromy was kept only in the setting, in the framework of continuous sublevel sets of functions, and but it has not to stay there. I mean, it has also an algebraic counterpart, and we can observe it wherever we want.
Right. Thank you.
So, any other questions from the audience?
I will have one. Hi, so I'm interested in Pareto sets in computationally. I know you worked on it in your thesis. Like sometimes we have, if we imagine some computable space, like a triangulated sphere or something, then we can use multi-persistence to analyze it, and there are multiple simplices which can appear at different times, but they all correspond to some same characteristic, if we could say it like that. Do you think monodromy could somewhat characterize those Pareto sets, those characteristics which all kind of fit together, but which appear at different times? Like in your example, you have characteristics, classes H and G, but they kind of merge together. Could you characterize those using monodromy?
Yeah, if I understand well, you have to translate everything. Like, I mean, you have when you have a Pareto area of your triangles, it's kind of an expansion of these generators. I mean, you have a front. And I feel that monodromy is not always there whenever you have two fronts merging, interacting. But there might be monodromy whenever there is a delay between the very first comparable moment where you have two different Pareto fronts, like this moment is the very first moment where you have these two Pareto parts merging, but there you don't have the relation. I mean, there in the very first moment you observe two separated parts still alive, and then there is a delay. I mean, the relation is when there is the effective merge of the two Pareto. So I see monodromy as related to the interaction between Pareto fronts, Pareto lines, but it's not always there. It depends if I have the two Pareto becoming one in the very first moment they can, or after. There is this delay, and this is making monodromy. Because if I put the relation here, there is no monodromy anymore.
Yeah.
And the difficult part is to theoretically connect all the results you have with Pareto cells, Pareto triangles, and something like that, extended Pareto grid in other contexts, and the algebraic setting, because we are talking all about the same things, but this kind of result, if we are talking about summands in a decomposition of a modules, it's very powerful to have the algebraic setting, but of course I'm not taking into account all the problems I can have with the triangles.
Thank you.
You're welcome.
Very interesting. Do we have any other questions in the chat or from the audience? Don't see anything. I just see like one message, but there's no question attached. So if not, I would say let's thank the speaker again, and let's
Thank you for inviting me.
yeah, thank you very much for being here.